CCSP exam practice questions. Domain 2, Cloud Data Security. 2. Question 1. A security architect is designing a cryptographic system for a large organization with 10,000 employees who need to communicate securely with each other. Which of the following best describes why asymmetric encryption would be preferred over symmetric encryption in this scenario? A. Because asymmetric encryption is faster than symmetric encryption for large volumes of data. B. Because symmetric encryption would require managing nearly 50 million encryption keys. C. Because asymmetric encryption provides better confidentiality than symmetric encryption. D. Because symmetric encryption cannot ensure message integrity between users. Correct answer. B. Explanation. This question tests understanding of key management challenges in symmetric versus asymmetric cryptography. For symmetric encryption in a large organization, the number of required keys follows the formula NN1-2, where N is the number of users. With 10,000 employees, this would result in 49,995,000 keys, 10,000 and 9,999 2, making key management extremely difficult. In contrast, asymmetric encryption only requires 2 keys per user, public and private, resulting in just 20,000 total keys for the organization. While asymmetric encryption is actually slower than symmetric encryption and both can provide confidentiality and integrity, the key management advantage makes it the preferred choice for this scenario. Question 2. Which of the following statements correctly describes a characteristic of cryptographic non-repudiation? A. It can be achieved using either symmetric or asymmetric encryption algorithms. B. It allows the sender to prove they didn't send a particular message. C. It ensures that encrypted messages cannot be modified during transmission. D. It allows the recipient to prove to a third party that a message came from the alleged sender. Correct answer: D. Explanation. This question evaluates understanding of non-repudiation as one of the 5 goals of cryptography. Non-repudiation specifically means that the recipient can prove to an independent third party that a message actually came from the alleged sender. This is only possible with asymmetric encryption and digital signatures, not with symmetric encryption, where both parties share the same key and could forge messages. Non-repudiation is different from integrity, which prevents modification, and is not about proving what wasn't sent, but rather proving what was sent and by whom. Question 3. A cloud security engineer is implementing encryption to protect sensitive data throughout its lifecycle. Which state of data is most challenging to protect using encryption? A. Data in transit between cloud services. B. Data at rest in cloud storage. C. Data in use within application memory. D. Data in backup archives. Correct answer: C. Explanation. This question tests understanding of the 3 states of data, at rest, in transit, and in use, and their encryption challenges. Data in use presents unique challenges because it must be decrypted in memory for applications to process it, making it potentially vulnerable to memory attacks. Data at rest, including backups, can be effectively protected using storage encryption, while data in transit can be secured using protocols like TLS. However, protecting data while it's actively being used in memory requires specialized techniques and remains one of the most challenging aspects of data protection. Question 4. Which cryptographic property ensures that changing a single bit of plaintext results in changes across a large portion of the ciphertext? A. Confusion. B. Diffusion. C. Obfuscation. D. Entropy. Correct answer: B. Explanation. This question tests knowledge of fundamental cryptographic properties. Diffusion is specifically defined as the property where changing a single bit of plain text should produce changes that spread across a large portion of the ciphertext, ideally changing at least half of the ciphertext bits. This is different from confusion, which hides the connection between ciphertext and key, obfuscation, which makes code or data unintelligible, and entropy, which relates to randomness. Diffusion is an essential property for strong encryption algorithms as it helps prevent pattern analysis. Question 5. What is the primary limitation of pseudo-random number generators in cryptographic applications? A. They produce numbers that are too complex for encryption algorithms. B. They cannot generate numbers quickly enough for real-time encryption. C. They cannot generate truly random numbers because the output is deterministic. D. They require too much computational power for practical use. Correct answer, C. Explanation. This question assesses understanding of random number generation in cryptography. The fundamental limitation of pseudo-random number generators is that they cannot generate truly random numbers because computers generate these numbers through deterministic processes. The numbers always come from somewhere using complex series of inputs and mathematical functions. While they can produce numbers that are very close to random, they are not truly random. This limitation is important in cryptography, where randomness is crucial for key generation and other security operations. The other options present incorrect limitations. PRNGs are efficient, fast enough for encryption, and produce suitable complexity for cryptographic use. Question 6. A developer is implementing encryption to protect sensitive user data. When considering the 5 goals of cryptography, which goal would be most appropriate for creating a unique, non-reversible value from a social security number? A. Authentication. B. Non-repudiation. C. Obfuscation. D. Integrity. Correct answer. C. Explanation. This question tests understanding of the 5 goals of cryptography: confidentiality, integrity, authentication, obfuscation, and non-repudiation, and their appropriate applications. Obfuscation is specifically defined as making data unintelligible, including to the system itself, which is exactly what's needed when creating a unique, non-reversible value from sensitive data, like a social security number. This is different from authentication, verifying identity, non-repudiation, proving message origin, or integrity, preventing unauthorized modifications. The goal is to create a value that can be used for reference while protecting the original sensitive data. Question 7. In a symmetric encryption implementation, Alice and Bob share a secret key for secure communication. If Charlie joins their group, how many total symmetric encryption keys would be required for all 3 individuals to communicate privately with each other? A. 2 keys. B. 4 keys. C. 3 keys. D. 6 keys. Correct answer, C. Explanation. This question tests understanding of symmetric key requirements for group communication. With symmetric encryption, each pair of users needs a unique shared key for private communication. In this scenario, Alice and Bob need 1 key, Alice and Charlie need 1 key, Bob and Charlie need 1 key, for a total of 3 keys. The formula for calculating the number of required symmetric keys is nn1, 2, where n is the number of users. With 3 users, this equals 3 to 2, 2 is 3 keys. This illustrates the key management challenge with symmetric encryption as group size grows. Question 8. Which cryptographic goal ensures that if Mallory intercepts an encrypted message between Alice and Bob, she cannot modify the contents without detection? A. Confidentiality. B. Non-repudiation. C. Integrity. D. Authentication. Correct answer. C. Explanation. This question evaluates understanding of the goals of cryptography. Integrity specifically protects messages against unauthorized modification and ensures that recipients can detect if a message has been tampered with during transmission. This is different from confidentiality, which prevents unauthorized reading of the message, non-repudiation, which proves message origin, and authentication, which verifies identity. In this scenario, integrity mechanisms would allow Bob to detect if Mallory had modified the message intercepted during transit. Question 9. A security architect needs to implement encryption for a system where data must be protected in multiple states. Which state of data would be most appropriate for using symmetric encryption due to performance considerations? A. Data in memory being processed by applications. B. Data at rest in long-term storage. C. Data in transit between internal services. D. Data being transformed for obfuscation. Correct answer. B. Explanation. This question tests understanding of encryption performance characteristics and data states. Symmetric encryption is generally faster than asymmetric encryption and is well suited for encrypting large volumes of data at rest in storage systems. While symmetric encryption can be used in other states, performance becomes especially important for data at rest due to the volume of data typically involved. Data in memory often requires specialized protection techniques, data in transit often uses hybrid encryption approaches, and data transformation might require specific algorithms based on the obfuscation goals. Question 10. When implementing a cryptographic system, which property ensures that a change to one bit of the encryption key affects multiple bits of the ciphertext, making it harder to crack? A. Obfuscation. B. Diffusion. C. Confusion. D. Entropy. Correct answer. C. Explanation. This question assesses understanding of fundamental cryptographic properties. Confusion is the property where every bit of the ciphertext must depend on more than one bit of the encryption key, hiding the connection between them. This is different from diffusion, which spreads changes in plaintext across the ciphertext, obfuscation, which makes data unintelligible, and entropy, which relates to randomness. Confusion is crucial for cryptographic strength, as it makes it more difficult to determine the key even if an attacker has multiple plaintext ciphertext pairs. Question 11. What is the primary reason that asymmetric encryption cannot be used alone for encrypting large volumes of data in cloud storage? A. It requires more complex key management. B. It is significantly slower than symmetric encryption. C. It cannot ensure data integrity. D. It requires more storage space for keys. Correct answer. B. Explanation. This question tests understanding of the practical limitations of asymmetric encryption. The primary limitation of asymmetric encryption is its computational overhead and slower performance compared to symmetric encryption, making it impractical for encrypting large volumes of data. While asymmetric encryption does have more complex key management, this is actually an advantage over symmetric encryption. The solution in practice is to use hybrid encryption, where symmetric encryption protects the data and asymmetric encryption protects the symmetric key. Question 12. In the context of cryptographic operations, which statement best describes the relationship between security strength and resource utilization? A. Stronger encryption always requires more processing power but less memory. B. Resource utilization decreases as security strength increases. C. There is no correlation between security strength and resource usage. D. Generally, stronger encryption requires more processing power. Correct answer, D. Explanation. This question evaluates understanding of the fundamental trade-off between security strength and computational resources in cryptography. As we increase the security strength of cryptographic operations through larger key sizes, more complex algorithms, or additional rounds. We generally require more processing power to perform encryption and decryption operations. This creates a practical trade off between security and performance that must be considered when designing cryptographic systems. The relationship isn't specifically about memory usage, and there is indeed a clear correlation between strength and resource usage.